Hi everybody, the purpose of this video is to do some initial explorations of developing Android apps using two important and interesting paradigms for communicating and coordinating among your application components, be they internal or distributed. Here we're just going to get started looking at these things in a non-distributed way, and they can then be generalized to more distributed architectures. So for example, the familiar click counter, you could envision a click counter that involves multiple devices at different locations, for example at different doors of a soccer stadium, and they would keep track of the same count to make sure that we're not exceeding the capacity of that stadium. So here, though, it's just a single click counter app assuming a single door, and we're still using these paradigms, looking at the two examples, one for each paradigm, to enable this kind of communication among these internal components within the app. And we'll start with RxScala, which is a Scala version of the RxJava library developed by Netflix, which is basically a Java version of Eric Meyer's Rx.net reactive extensions. And really the key point here is to think of the observer pattern in a different way. So this is kind of an evolution of the observer pattern in a more systematic way, and there's the paper by Mark Nodersky and his collaborators called Deprecating the Observer Pattern. So the intent is here to move beyond the conventional, in quotes, observer pattern, and to take things to another level where we can apply useful functional programming techniques to make things more systematic and more concise. So let's take a look. I'm not going to demo the apps because their observable behavior is at least supposed to be exactly the same as that of the ordinary Scala version of the click counter. So you've seen that a gazillion number of times, so no need to demo those again. But instead we'll take a look at the architecture, the internal architecture, and the code. So basically what we're doing here is we're starting with the UI. So we're going to look at the main activity as usual first, and this main activity, and as usual pay attention to my Scala doc comments, which are intended to explain the architecture a little bit. So what we're seeing here is a kind of stripped down main activity that is responsible just for the lifecycle methods here on create and on start, and it mixes in some traits that we're about to look at. So it mixes in the observable view trait, which is going to be responsible for handling user triggered input events, and then the view updater, which is responsible for, as the name suggests, updating the output view components per the adapter's instructions. And in fact, the main activity is responsible just for, as part of the onCreate lifecycle event handling, to connect everything so that we get the picture on the right. And I'll explain this picture in a little bit more detail. So we're going to come back to the main activities on create method shortly. The other component that's important, that's down here, that's in some sense it's an indispensable component, in the sense that this makes sure that we keep track of the counter value across interactions with the user, because everything else but this value holder is stateless here. So this is the only place where we have a variable. All right, so let's take a look. And we'll take a look at this reactive view file, and that's where these adapter mix-ins are defined. So the observable view, this is pretty clear. This is one piece of the adapter for handling the input events. And as usual, it has these methods corresponding to the 3 buttons. And what it does is, with the help of this so-called subject, which is an RxScala, RxJava thing, it converts the button presses to what I would call semantic events in the form of kind of a standardized event stream. So whenever the onIncrement method is invoked, presumably because the user presses the increment button, then we invoke the onNext method on the subject with an argument value of this case object increment. So that's just a case object, basically just a symbol, meaning that it's an increment event as opposed to some other kind of event. Okay, and then the same kind of stuff happens for the other events. The question is, what does the subject do for us? Well, the subject is something that we can actually subscribe to. And it basically generalizes this idea of an event source. So the subject is a kind of standardized, generalized event source, and then listeners or observers can subscribe to this. And the view updater is an observer, and here the notion of observer is generalized, so we have to then parameterize this by saying what kind of things this view updater wants to observe, and we're providing this generic type argument, and this says it wants to get pairs of an int value combined with a model state. So model state corresponds to the abstract click counter or abstract bounded counter state as described in the Cedar chapter. And what you can see is here it checks whether that model state is full or empty. Okay, so it's that type of model state of the internal bounded counter. And what this does is when it hears from whoever sends it the this event, which happens to be this pair of an int value and a model state, then it looks, so it says, okay, well, let's break that incoming argument representing the event up into those 2 pieces, the value and the model state, and let's set the text of the value display to that value. And then let's enable or disable the increment and decrement buttons according to the model state. So as usual. Okay, well, what do we have now? Well, we just basically saw these upper layers. So if we look on the right, obviously when we interact with the app, there are these buttons and the text views for the input and output respectively. And the buttons, let's say increment buttons on click, goes into the, let's say, on increment method here of the observable view, which we're looking at on the left. And that just basically sends on an event using this dashed arrow. And we'll look shortly at where the event goes. And then on the incoming side, so the dashed arrow comes into the view updater here, and then that does things such as set text, and it's not showing the solid arrow that invokes the set enabled method on the button. That will be a little enhancement to this diagram. So, but the idea is the view updater invokes methods on the view components. Okay, so now we need to look back at the main activity and see what is connected to these guys. Well, first of all, okay, these two traits we just looked at, observable view and view updater, are mixed into the main activity. That means they're kind of inherited, and the main activity inherits the subject, and we see that here. So the other thing we have, really the remaining thing that you haven't seen yet, is the counter model instance. We've already seen that there's a value holder instance, so that's that. And that is an observer that is interested just in ints. Okay, and what will it do when it gets an int event? So the onNext, just to emphasize this more clearly, onNext is the generalized event handling method. So instead of onClick or on state changed or any of those kinds of things, we're using onNext for every observer that is part of this Java RxScala, or just simply Rx paradigm. Okay, so onNext is the generalized listener method, and there are a couple of other methods. There's onError and onDone, and those are for, let's say, the onDone is for event streams where at some point there will be no more events. So the onDone can be used to indicate that. But here we don't need that. We only need to worry about the onNext. And the value holder simply stores whatever value it receives as an incoming event from the onNext method invocation. So whatever it receives, it stores that in the variable value. All right. So now, let's make this whole thing work, okay? First, maybe it's better to look at the reactive bounded counter model first, and then we'll look at how it all fits together. So the reactive bounded counter is a stateless bounded counter, meaning it doesn't store the value because that's the value holder's job, and it responds to incoming events by sending back a response event. So this is both an observer and a subject. So it says here, it extends observer, so it's interested in incoming int values combined with an input event. And the input event, we'll scroll up a little bit, those are the things that the observable view converts button presses to. So we can see this here in the top left corner. So these are just case objects, the increment, decrement, and reset, that extend this common input event trait. And here are the abstract model states we were looking at in conjunction with the view updater. So we have empty, counting, and full corresponding to the bounded counter states. Okay, what the reactive bounded counter does, well, it takes a min and a max. Those are the bounds for the counter that are instance specific. And these are, by the way, public instance variables. That's what the val does. And the reactive bounded counter is an observer, and it has an observable that we can access using this method. What kind of observable is it? Meaning, what kind of response events does it produce? Oh, int values combined with the model state. So it receives an int value combined with an input event, and it responds by giving another int value and a model state. Okay. So what are these different things coming in and going out? Well, the incoming thing is, the incoming int value is the old counter value. And the input event says, well, increment, decrement, or reset. And then this reactive bounded counter processes this input and says, here's the new value based on the kind of input event you just gave me, and here's the corresponding abstract model state. Okay? So it basically responds to these incoming events by returning the information that correspond to the expected bounded counter behavior. And let's see. All we really need to focus on now is the onNext, because that's again where the reactive behavior lies. And in this case, this is, as I mentioned, both an observer and an observable. So when the onNext method is invoked, then it'll typically respond by telling the subject that it has up here, that is exposed as the observable. It tells it to respond by sending out an event, and it does that by invoking onNext on that subject. So let's take a look at the logic. So we again break down the incoming event into the old counter value and the input event, and we'll say, well, we'll calculate the new value, the tentative new value. So that's really the heart of the logic right here. Figure out the new value. So if it's an increment, we return the old value +1. If it's decrement, we return the old value -1. If it's reset, we unconditionally return the min. And that's now value. So there's one more step though, because before we actually respond with this value, we have to make sure that this new value satisfies our data invariant, which means it has to be within the bounds. And that's right up here, as usual. And we'll say only if the new value that we computed tentatively satisfies the data invariant, then, well, we'll compute the corresponding abstract state, right? If it's full, then the abstract state is full. If it's empty, then the abstract state is empty. Otherwise, we're in the counting state, in that middle state. And then we'll fire the response event through our subject, this auxiliary object subject that others can listen to. So that's all there is to it, you see? So it doesn't actually worry about storing the new counter value, because we got the value holder for that. Okay? So that's that. And now we can meaningfully look at the main activity, which simply then wires everything together. And then we'll take another quick look at the diagram on the right and make sense of it all. Okay. All right, so the activity is already equipped with an observable view and view updater, because we mix these in as traits. Then we create the instance of the value holder, and we create an instance of the bounded counter model. Okay. Now we need to wire things together. So this subject is the observable view, and we want whom to receive the events coming out of the observable view? Well, the counter. So we'll say, let's connect the counter to the subject, meaning now the counter will receive the events coming out of the observable view. There's one thing though. The observable view just produces the semantic input events, increment, decrement, reset, and the counter also wants the current or old value, and that's why we need to attach, and this map does that. So map is a higher order function that takes a collection, or in this case an event stream, meaning really here it does this for every event that comes through it. And it takes, for each value in the collection or stream, it applies a function to that value and basically thereby transforms the collection or a stream to a new one where each old value is basically sent through this function and then turns up as a new value as the result of this function applied to the old value. So it basically applies a function to each item in the collection or stream, and in this case the function is given in this very kind of concise Scala shorthand. So what this really means, the underscore means the argument, which would be the input event. So it says, well, let's take the argument, this input event, and transform it to a pair where the first item is the current value of the holder and the second value of the pair is the input event. And remember, that's exactly what the counter was observing, a pair of int and input event. So this is exactly the kind of stuff that the counter wants to receive. And by the way, this is all statically typed, so if it didn't fit, then the compiler would tell us. Okay? Alright, so now what we just established is this dashed arrow from the observable view to the reactive bounded counter. And this access to the holder value, that's this solid arrow here, from the observable view to the value holder. Okay, very good. Now we need to set up two more dashed arrows, these two here. And what we're going to set up first is the one in the middle. And we're now setting things up so that the new value gets stored in the value holder. And we're doing that by subscribing the holder to the observable of the counter. Okay, but there's still a mismatch, right? The counter produces the new value combined with an abstract model state. And the holder only wants the value. As we see here, the holder is an observer of int. Well, no problem, we'll use another map. And this function here is a shorthand for saying, take only the first item of a pair. So if we have a pair of int and anything else, or even other things, this could work with a pair or a larger tuple, we're only taking the first component of that tuple. So this means whatever we get from the counter, coming out of the counter, we'll just take the first item, which happens to be the int value that we want to store in the holder. And that is represented here. So meaning we are hooking up to the counter, but we're transforming, this is kind of a smart dashed arrow, a smart event-based connection that does a little transformation, which is just transforming that pair with the first component being an int to just the int. Okay, so now we got this arrow in the middle, and then finally we'll just do a very simple hookup of the main activity, in particular the view updater, which really wants both of the things that are coming out of the counter. So we can do a straight subscription without any transformation. So to illustrate that, we just have here map underscore, meaning really the identity, meaning it doesn't do anything. All right, so now we have the complete picture, and again, round trip information and control flow here is user presses button. The observable view converts that into a semantic input event, such as increment. And this smart dashed arrow, the smart event connection, attaches the current counter value from the holder to that input event, and that goes to the reactive bounded counter. Reactive bounded counter responds by sending back the new counter value plus the corresponding resulting abstract model state, and it sends those to anybody who's subscribed, and that means the value holder and the view updater. The value holder only gets the int value because the this dashed arrow throws away the rest, so it's a projection, so to speak. And the view updater gets exactly what comes out of the reactive bounded counter, and then it updates the view components accordingly. All right, so that's the complete round trip flow here. And again, of course, this is a very simple example, but I think we're seeing the value of the paradigm in being able to express our event sources and event listeners in very standardized, clear ways without actually having to introduce new event types and corresponding listener interfaces. Remember in the stopwatch and the corresponding project, we had a lot of those. So we could probably save quite a bit of effort and code and maybe improve the clarity by switching to this type of paradigm using this kind of library. Just using standardized interfaces and these standardized observables and observers. And let's see, the other thing is that we achieve thereby also a very nice separation of concerns. So for example, we were able to separate completely the concern of handling incoming events, updating the view, maintaining the mutable state. That's the value holder's job. So it encourages a nicer separation of concerns, and as by now I think you're quite familiar and comfortable with, this makes testing easier. And you can take a look at the test code. So there are a bunch of different kinds of tests here, and it works pretty well. So anyway, so this is it as far as the reactive extensions paradigm is concerned. And we'll take a quick look at another version of the click counter using Akka actors. And actors are another way to deal with communication and coordination among components in a very disciplined way, where we kind of shift away from manipulating state, mutable state, using methods by encapsulating the state within an actor in such a way that the actor processes at most one message at a given time, and it thereby protects the encapsulated state from concurrent modification. Of course, this is only one of many uses of the actor paradigm, but it is one important use, assuming that we have mutable state in these kinds of applications, like the counter value. You really cannot get around storing that somewhere so that the user won't have to input the old value, right? That's really the only way you can get away without storing the current value in the application. Now, this sounds funny, but actually there are paradigms that work kind of like that. So the representational state transfer, or REST paradigm, pretty much works like that. In fact, it's one way of using REST. Okay, so now let's take a look at this actor-based example. Well, let's first take a quick look at the type-safe tutorial for this, and just to become a little bit familiar with the notion. So here's a let's see if we have to reload this. Okay, here it is. So here's a little hello world actor whose job is just to create an instance of this other actor, which is a greeter, like a Walmart greeter, and it then sends a message to this actor, and these are messages in terms of the actor paradigm. So there's this bang operator, the exclamation mark, and that means tell, or tell the actor something. That means sending a message to the actor, as opposed to an object-oriented method invocation. So here we're creating the greeter actor, and then we're telling it to greet. And here the receive is the method where we're describing the way the actor behaves in response to incoming messages. Whenever the actor receives something that someone else tells it, that is handled by the receive method. And here this actor is assuming just a done message, and in that case it'll shut itself down. Okay. So we're really just scratching the surface here. There's a lot more, of course, to the actor paradigm. And here's the greeter actor. So this is very simple. It also has these two case objects here, similar to the semantic events in our preceding example. And the receive method of this greeter actor is here. So it just is interested only in greet messages, and when it receives such a message, it says it prints something and then responds to the sender a done message with a done message. Okay, so these tell or bang operations are one-way sends, so this doesn't wait for a response like a method invocation. So there are some similarities to the reactive paradigm, but this is very general, the actor paradigm. So let's see now. This is extremely simple, and then to start it up, really, you don't even have to write a main method, because all you need to do is start it using a standardized Akka main method and provide the class of the main actor as the argument, and then it'll basically instantiate this main hello world actor and invoke the pre-start lifecycle method. So these actors also have a little bit of a life cycle, and the pre-start serves as this kind of entry point. So that's how we don't need to write our own main method. So the Akka main will just create this actor and then invoke the pre-start, and that's where execution starts. So in particular, that's where the greet event gets sent to the greeter. Then, as we saw, the greeter will respond by sending a done event back to the sender, and the sender is this hello world actor. So it receives this, shuts down, and execution stops there. So this is a very simple interaction of just sending one event to the greeter actor and then receiving an event back or a message back and then shutting down. Okay, so now we're going to look at the Akka version of the click counter, and that one of course has a sequence of interactions with the user. So this is not just a quick exchange of events or messages and then shutting down, but rather an ongoing thing until you turn the device off or exit the app. So let's take a look. Here we have, let's see, the UI. We have a main activity. And what we're doing here is we always have to instantiate some kind of actor system unless we use the Akka main method, but we don't have that option here, right? We have to follow the main activity, Android main activity lifecycle, so we'll have to do some of these things on our own. And here we're creating an instance of the adapter actor. And here we're performing a little bit of adapter work. This should probably be a separate trait. That's a possibility. So that it's taken out of the main activity, but no big deal here. So what we're doing here is transforming the user-triggered input events to messages we're telling the actor. So with a bang operator. Okay, so very similar to what we see over here. And let's look at this actor now. What does this actor do? Well, it lives right here in the UI layer because it's really an adapter. And what this does is basically handle the response events coming back from the model actor, and we'll look at that shortly. But what happens to the incoming input events? Well, those it actually just passes through. So that's that last case at the bottom. Okay, so if it gets these events corresponding to the button presses, it just passes those on to its child actor, which is the model actor. Okay, so similar to the Rx example here, we have an actor, kind of a component as the model that follows the corresponding paradigm that we're studying. Okay, and the model actor will take these incoming input events and then will respond again by sending back stuff like the new counter value and the abstract model state that resulted from the interaction. Okay, but this bounded counter actor will actually also maintain the current counter state, counter value, the actual int value. So there isn't anymore a separate value holder. This is really more like our original simple bounded counter, but with the model, instead of being just an ordinary object, this is an actor that just communicates through these messages. Okay, so let's take a look at the counter model very quickly. So here it is. Here is the actual mutable value. And what else do we have? Oh, here we do have a few case objects again for the semantic input events and for the model states. Now let's look at the behavior of the actor And that is, of course, provided in the receive method. And it's very simple. There are only three possibilities: increment, decrement, and reset. And the data invariant is encoded in these various conditionals. So there isn't the separation we had in the reactive one, where we tentatively created the new computed the new value, and then checked the data invariant. Here we're just basically we're using a slightly different style. So we're checking this part of the data invariant here. So we're incrementing only if we're below the max, and then we're unconditionally responding with a resulting value and with the corresponding abstract model state. We could, of course, respond conditionally. Then it would be much closer, actually, to the other example. So that should be an enhancement I can make. All right, so what we're seeing here is the response consists of sending out two things separately. So there are these two separate tell statements. One is, or expressions. One is to tell the value, and the other one is to tell the abstract model state. And in all cases, it's structured in that same way. All right, so now back to the adapter actor. Now we can close the loop and make sense of the adapter actor. So these case branches are based on, they could be based on values and or types. Okay, so if we get back one of these abstract model states, we do the usual thing, which is enabling and or disabling certain buttons. And if we're getting back a value, we're just updating the text view for that. So in fact, see how this actor doesn't care in which order it receives the value or the abstract model state. Okay, so once again, to see the round trip thing, the input button presses correspond to these methods, these event handling methods, and they translate the button presses to messages where we're sending these abstract input events or semantic input events to the adapter actor, and everything else is handled in the adapter actor. In particular, these input events are handled by passing them through into the model, and then the adapter actor just expects these responses back from the model. So, and then invokes methods on the view components. Okay. So again, here we're achieving a relatively loose coupling. Although there are these direct references in the sense that the adapter actor knows about the model actor, as opposed to the Rx version where everything was just in terms of observables to which the connection to which the listeners were subscribed outside of the observable. And that is an enhancement I'm trying to figure out how to do. So I want to be able to inject the counter actor instance into this adapter actor instance, and I will also need this to enable testing. Because right now this is exactly how you don't want to do it, where a dependency, so in this case the adapter actor depends on the bounded counter actor, it refers to the bounded counter actor, where this dependency is hard-coded. So as we learned in Software Engineering Radio episode 2, among other places, that's how not to do it. So we need to somehow bring dependency injection back into this picture. And of course, in the Rx version, we didn't really need explicit dependency injection because everything's already so loosely coupled in terms of the subscribe method. So the subscribe is really kind of the dependency injection when you're using observer observable. So here we don't quite have that yet, but it's going to be possible in some way to inject the child actor so that for the app itself it can be an instance of this bounded counter actor, and for testing it could be maybe an instance of a mock actor. Okay, so in sum, we've scratched the surface by looking at reactive extensions based click counter example and an Akka actor based one, and the next steps will be that I'm interested in pursuing is to see how these two paradigms can be used for actually distributed systems, where again we might have multiple click counter apps instances running on different devices that actually communicate and make sure that they're all maintaining the same shared counter value. So there will be some interesting questions to consider there. All right, so this is it, and we'll be in touch soon.